All right. I am back. Originally, I was like, I think I'm gonna stream one of my other math books that I've been working on in my trigonometry book, and then I thought about streaming some calculus. But I want to catch up quite a bit on this book because I am taking this class later in January. So what we're going to do is we're just going to try to cover a lot of ground. And the reason that I've been gone for the past 3 weeks is work, a lot of work. So, both as a skating coach and as a landscaper, been very busy all around, which is great for me. But yeah, let's do this. Just a second here. Make sure that everything is running smoothly. And yeah. Okay. So right now we are reading section 2.6, that's page 50, and we're going to read through it, and then afterwards I am going to do the equations. In contemplating the truth table for P implies Q, or P if and only if Q, you probably noticed that P if and only if Q is true exactly when P and Q are both true or both false. In other words, P if and only if Q is true precisely when at least one of the statements P and Q or not P and not Q is true. This may tempt us to say that P if and only if Q means the same thing as P and Q or not P and not Q. To see if this is really so, we could write the truth tables. So let's find out. They have a truth table down here, but we're going to write this and work our way through it real quick. So we're going to say P, Q, not P, not Q, P, and Q, not P, and not Q. And then we have P and Q, or not P and not Q. And P if and only if Q. Okay, so let's see what this gives us. So there's only 4 variables because the outcomes between P and Q, there's only 4 really that could happen. We have true, true, false, false, true, false, true, false. Okay, not P, so we're going to say false, false, true, true. Not Q, we're going to say false, true, false, true. P and Q, true, false, false, false. Okay, let me just make sure that P and Q. So far, so good. I'm not looking at the truth table as I'm writing. I'm just solving this on the fly. But if you can look on page 50, I'm just reviewing the work after I do it. So I might make a mistake and make a few corrections, just letting you know. Okay, so we have not P and not Q. So they both have to be true. And that's only in the bottom, which is going to be true, not P and not Q, and everything else is false. False, false, false. Yes, and then we're going to say P and Q, or not P and not Q. So we have P and Q, or. So basically we have this one and this one, and we're saying an or between them. One or the other has to be true. So we're going to say true. I have false, false, true. Okay, good. And the last one, P implies Q if and only if Q. So if we go back to P and Q right here, that means if both are false, it's true. Just remember that. When you have an implication statement of the type of if and only if, or P implies Q or Q implies P, what happens is, keep in mind, if both are false, then the original statement hasn't been challenged. This is particular to the implication type, the implies, okay? This type or this type. Keep that in mind, very important. So true, because both are false. The truthfulness of that statement has not been challenged. This is false, because one is false. And then the final one is both true, so it's true. So then if you could look at it, this and this is the same. So yeah, the book, and that's what it has in the book. Perfect. And you can see it right there on page 50. By the way, to download the book, it's in the video description. It's part of Creative Commons. Get the book. It's a great book. Download it. It's free. The table shows that P if and only if Q and P and Q, or not P and not Q, have the same truth value no matter the values for P and Q. It is as if P if and only if Q and Q and P and Q, or not P and not Q, are algebraic expressions that are equal no matter what is plugged into variables P and Q, where we express the state of affairs by writing. I'm going to do some writing here. Okay, so we're going to write, let's go to this page, we're at 2.6. All right, and it is P if and only if Q is equal to, let's see here, P and Q, or not P and not Q. Okay. Now, so here we go. So, and saying that P implies Q and Q implies P, and that's if and only if Q. P if and only if Q, and P and Q, or not P and not Q, are logically equivalent. In general, two statements are logically equivalent if their truth values match up line for line in a truth table. Logical equivalence is important because it can give us different and potentially useful ways of looking at the same thing. As an example, the following table shows P implies Q is logically equivalent to not Q implies not P. Well, let's establish that ourselves first. Without staring at that table, we don't want to know what the result is. We want to find the result. Okay. Not P, not Q. PQ, not P, not Q. And then we're going to say not Q implies not P. And then last one, we're going to say that P implies Q. So what are we looking for here right now? We want to know is P implies Q, is this equal to not Q implies not P? That's what we want to establish. P, yes. Okay, so this one right here. Well, let's find out here. We're going to say true, true, false, false. Say true, false, true, false. We're going to say false, false, true, true. And then we're going to say false, true, false. By this point, you should be comfortable with telling what's P, what's not P. The values for P can be, you could write them in whatever order you want. We're trying to write them in an organized manner to make it easier for us to do all the other truth tables. We can write FFTT. We can start with the falsehoods and then the truthhoods. But the way this is organized, it's just for convenience. But the relationships do matter, right? What is P if P is true? And then not P would obviously have to be false. These will always invert. Now, we're going to say not Q implies not P. So right away, let's find the falsehoods. When they're both true, then they're true. When they're both false, they are going to be also true. So false, false in the beginning, that's true. False, true is false. True, false is false. False and true, true is true. And P implies Q. Again, if they're both false, it's true. If they're both true, it's true. If one is false, it's false. So we can see that this is logically equivalent to that. If you look at the book, yes, that is exactly what's in there. So right away, we've established something, all right? We established that this is true, right? That's correct. All right, the fact that P implies Q is equal to not Q implies not P is useful because so many theorems have the form P implies Q. Okay, so what they're telling us here, this is going to be for proofs. Remember, the thing we're working toward, we're not even close yet, and that's proofs. It's where you prove for every outcome a statement, and oftentimes if the statement is or mathematical truth or we're trying to work with something like that, and then we're trying to prove something. Sometimes it's very hard to prove the truth of something, but you can prove the inverse of it, or you can falsify it. In other words, if you can show that the inverse is true or false, and then that way you can, in a roundabout way, you could achieve the results you wanted. Anyway, by proving the inverse of it, so to speak. Anyway, we'll see that later. Don't worry about it too much. It doesn't have to make sense right now. Anyway, so here we go. As we'll see in Chapter 5, proving such a theorem may be easier if we express it in the logical equivalent form of not Q implies not P. The two pairs are logically equivalent statements, in particular are significant enough to have a special name, De Morgan's laws. All right, so if we have a statement that, by the way, here's what we're trying to say here. This part's kind of important. Don't have to worry about it now until Chapter 5. But if we have a statement, say P implies if you get grade A, you will graduate. A and Q. Let's just say that, right? Grade A and graduate. So we're going to say if P implies Q, P implies Q, so this, right, that's equivalent. This is equivalent to not P if you don't get grade A, you won't graduate. Okay, that is right here. Not P implies not Q. All right, that's what we did right there. This is the same thing. So P implies Q is equivalent to that. So yeah, this is what we're going to be looking at. These kind of things where it's sometimes hard to understand where any of this is going anywhere. You just kind of have to roll with it. Just you're assembling. We're creating Lego pieces, so to speak, And later on, once we really have polished them out and they can all click back into each other, so to speak, we'll be able to build things sometimes in ways that are roundabout and unexpected and solve problems. It's really cool. But we really need all our pieces. Right now, we have many pieces still missing. So let's keep working on it. Let's keep building our rows. So now we have De Morgan's laws. De Morgan's laws, according to the book, fact 2.1. Not P and Q. This is where it gets flipped. If we take this and we spread this in like that, all we got to do is we got to flip this thing. We got to rotate that. So I just remember this from memory. Not P or not Q. All right, yes, and then we have not P or Q. Again, we can bring it in. We can drop it in on the P and we can separate them, but then it flips from an or to an and, not Q. These are logically equivalent statements. They are true, and that's another Lego piece for us. We can take these things and use them later. All right, De Morgan's laws, important. Now, but let's not take anyone's word for it. Let's prove it. All right, that's the whole point of this, is we prove things. All right, so right. Okay. Now let's do the usual drill. True, true, false, false for P. True, false, false. Okay. Not P is false. False, true, true, not Q. False, true, true. P and Q, they both have to be true. True. Everything else is false. False, false, false. Not P and Q. So we inverse it, so everything gets flipped. False, true, true, true. Not P or not Q. One of them has to be true. Not P or not Q. So we have false, true, true, and true. Both can be true in an or statement. It's not an exclusive or. So yeah, as we can see, we just proved it. We proved that this is logically equivalent to that. We just did that. That was fun. Okay. De Morgan's laws are actually very natural and intuitive. Consider the statement not P and Q. Not P and Q, which we can interpret as meaning that it is not the case that both P and Q are true. If it is not the case that both P and Q are true, then at least one of P or Q is false. Forgive me. In which case, not P or not Q is true. Thus, not P and Q means the same thing as not P or not Q. Okay. Okay, so we have... This is some good stuff here. De Morgan's laws can be very useful. Suppose we happen to know some statement of the form not P or Q is true. The second of De Morgan's laws tells us not Q or, sorry, not Q and not P is also true. Hence, not P and Q are both true as well. Hence, quickly obtaining this information can be extremely useful. Here's a summary of some significant logical equivalents that are not immediately obvious but can be verified with truth tables. Okay, so let's write these out. Okay, so we're going to say 2.1. By the way, 2.1, these are like, they don't necessarily align with like chapters. It's more like a fact thing or whatever. Sometimes, like, we're in chapter 2.6. This is a 2.1 counterpositive law. It's more like a fact. P implies Q is equal to not Q implies not P. Okay. So we're just going to take these on face value. We could write out a truth table for all of them, but it would just take a while, and we don't need to do that. If it's in the book here and it says it's true, and the book's been thoroughly vetted, yeah, we can go in and double check everything. But our goal is to get through the book, and at this point, we want to get all the stuff in our heads, because there is a lot of material to cover. Okay, De Morgan's laws, not P or Q is equal to not P or not Q. And this kind of stuff tends to appear on tests. So if you can't remember it and there's too much material to remember everything, you have to be able to like recreate it by writing truth tables. That's why they keep having us do truth tables, is because you can't remember every one of these formulas, and you have to be able to prove them even if you do remember. So that's what it's for. Remember, the and the ors get flipped if you distribute the not. Okay, and then we have 2.3. Okay, we have P and Q is equal to Q and P. So effect and cause both being true is the same thing as the cause and effect being true. So, or vice versa. And then cause and cause. Actually, this isn't exactly cause and effect. On an implication, you could think of it as cause and effect. This is more like fact 1 and fact 2. If both facts 1 and 2 are true, the order of them will not change. They both will remain true. If you have P or Q, if one of them is true, then you can change around their order, but at least one of them will still be true. That will not change. Now this is distributive. 2.4. Distributive laws. I'm going to take this a little lower so it doesn't. All right, so we have P and Q or R, so we have 3 statements, is equal to P and Q or P and R. So the P has to be true, or in this, because it's an and, in order for the truth table to match up, but it only needs one Q or one R. I mean, they could both be true, but at least one of them has to be true in order to get the same truthfulness of the truth table. All right. And then the other distributive law, here we go. And the same thing for the OR. If P OR, again, we're going to take Q and R. And it just needs one of them. And R. All right, that's good. By the way, distributive, associative, commutative laws, those come up a lot. This kind of being able to move parentheses around or the order around, it doesn't hold for all types of mathematics, but like especially when you get to linear algebra, you're going to see like cross multiplication, things like that. Some things hold. Now, don't quote me specifically which cases where distributive or associative laws are different, but just keep in mind that commutative, distributive, associative laws, they are fundamental ideas in mathematics, and they come up in a lot of different stuff. Anyway, just keep that in mind. Then we have finally associative laws. 0.5. P or Q and P and Q and R. Now the Q and R is, think of it as a single unit because that has to be true in one way or another. But we can move that parenthesis because and unites them in this sense. They all have to be true. Every single item that's part of that and set. I say P and Q and R. And then with the OR, same thing works as long as one of them is true. They give it that way. Or R. Now these things, like they're all provable. We can write truth tables. It would just take a while, but if you're curious, write out the truth table and see for yourself. Believe me, everyone who did all this for the books, they would have been proven and proven time and again, tested and retested. So yeah. All right, now, which isn't to say that there can't be an error. I mean, rarely, but it does happen. And usually an error is like a form of a misprint where they're writing like a question and they give you a value from, and then they might accidentally write the same value twice in two subsequent equations. That kind of a thing happens. Actually, if you look at my trigonometry stream, there was one case where it was very obvious where they simply wrote the size of something twice in a way that was, easily incorrect and provable. And you just watch one of my videos, and I showed it where the back of the book gave a different answer than what it was like. This was scientific notation, so it was like one of those things where it was like non-controversial or anything like that. It was just a simple misprint, and I showed where the misprint came from, where they had originally what they meant to say, and how they accidentally carried that over. Like those things happen occasionally, but it's very rare. Don't assume that just because something doesn't make sense, it's a misprint. All right, so. All right. Like, for example, I probably make about 100 mistakes for any misprint that I ever find. Probably more than that. All right. Use truth tables to show the following statements are logically equivalent. Okay. So we're going to say say P. And right away, we should know that there are three variables, P, Q, and R. So this is going to be 8 implies P or Q or P and, wait a minute. Now we could also say something to the effect of, by De Morgan's law, so and so is true, or by the associative or commutative law, such and such is true. So in this case, If we look at this right here, what they're doing here, I could write and say like by what term they use here? Fact 2.5. The above is true. True and is an let's see here. Right. By the fact 2.5, the above is true and is an example of the associative law. So yeah, there, and I solved the answer basically. But we're not gonna do that. You can do that if, I mean, like in cases where they don't have you, like you have to write out the truth table. But if it wasn't a condition of answering the question by having to write the truth table, you could call back to one of the laws. By De Morgan's law, so and so is true. You know, that kind of a thing. And this is more when we start writing proofs in chapter 5. Is we don't have to like just go into the weeds and prove everything via truth tables. We could just say, hey, by De Morgan's law, you know, we could assign P and Q and R to various statements, and then we can show them how they relate to each other, and be like, by De Morgan's law, by associative law, it's just true, therefore that. Okay, so let's actually do this though. P and Q and R, and then here. Wait a minute. Oh, I made a slight mistake here, didn't I? Yeah, okay, I miswrote that. Here's where I messed up. P and right. The associative law only works if all of the signs. This is more actually. Let me see here. Let me check real quick here. P and yeah, no. Let's get rid of that. So this will be true if under one condition. If this was associative law P and Q, they would all have to be here. Let me rewrite that to make this the below true, and then we're gonna answer that. So if it was like this, then that would be true by the associative law. Okay, so but we're not doing the associative law, we're just doing one of them. That's nothing to do with it. So now this is ands and ors. So those were all ands. And here we do have some ors. All right. So this is or and or. Okay. So we are saying to show the following logical equivalent, P and Q or R is equal to P and Q or P and R. So right, let's do it. We're going to go P, Q, R, and then we need to have Q and R. Actually, what do we need here? We will need Q or R, yeah. Q or R. And then we're going to need P and Q or R. And then we're going to need P and Q or P and R. Okay, let's remember there are 3 variables. Our n is 3. 2 to the power of n gives us a number of possible variations. So it's 8. 2 to the power of 3 is 8. So then that's what we're going to do. So we're going to go 4, true, 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 false, 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 false. We're going to divide that in half. We're going to go true, true, false, false, true, true, false, false. By the way, the reason why we're doing it this way is simply to keep it in an organized way. You can write in any order. You can start with R. You could start with Q. Doesn't matter. You could start with falsehoods and then put truth in the middle. You can go with P being true and false. But this is simply an organized way. And that way, it just makes our work that much easier. And if you write enough truth tables, especially starting with the simpler ones, you're going to quickly see why this makes sense. Okay, true, 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 false, 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 true, true, false, false, true, false, false, true, false, true, false, true, false, true, false. Okay, Q or R. One or the other or both must be true. Let's check that. Line 8 is false. 7's true, 6 true, 5's true, 4 false, 3 is true, 2 and 1 are true. Good. Okay, so now we're going to take this and we're going to add that with P. They both have to be true in an AND. You can't have one true, one false. That's an OR. So first is true, second is true, third is true, fourth is false, fifth is false, 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 false. So as you can see, because on an AND, if they're both false, it's still false. This is not an implication one. So we have 4, 5, 6, 7, 8 false. Okay, so only the first 3 are true. Okay, now we have P and Q. So we have, wait a minute here, P and R, or P and Q. So I didn't write those two, P and Q. Let's put them back here, P and Q, P and R. Okay, so it's just P and Q. They agree true, true, false, 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 false. Yeah, they only agree because it's an AND. They have to both be true. That's only the first 2 lines. So false, 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 false. Okay, P or R. The first lines and the third lines agree. Everything else is false. True, false, true, false, 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 false. Okay, let's check that. Yes, yes. Good. Now, we got P and Q or P and R. So one or the other or both have to be true. So first line is true. Second line is true. Third line is true. All the way it's false. False, false. 1, 2, 3, 4, 5, 6, 7, 8. And what do we got? Look at that. This and this are the same. We proved a logical equivalence. Nice. All right. So now we have demonstrated this. As far the way it works is they want us to demonstrate that it's logically equivalent. So technically we just did that. That by itself proves that the answer is correct. But I'm just going to look in the back of the book, see what they wrote. All right, section 2.6. Yes, okay, so then we have first 3 is true, all the rest is false. Yes, that is correct. Now, if you look in the back of the book, the part where this is page 300 for solutions. Now, again, we're only doing odds because we don't want to damage the integrity of the book as a teaching resource. So the ones that are in bold are the ones that they actually want answered. The rest is just a truth table to help you get there. So yeah, that's good. 1 is great. Let's go on. All right. 3. So we have P implies Q is equal to not P or Q. One of those two. So P implies Q. There's only 2 variables, so there's going to be 4 possible outcomes. Statement P and statement Q. What other ones do we need? We need not P. Then we need P implies Q. And we need not P or Q. Okay, so that should give us to get to the last part. So essentially, we want to prove that these two are the same. That's what we're going for. True, true, false, false. True, false, true, false. False, false, true, true. Hopefully by now, what I'm doing, the first 3 columns makes complete sense. If not, the not P has to be the inverse of P. And the Q is just we're writing what are the various outcomes. We want to know what happens when they're both true. What happens if they're both false? What happens if statement 1, or P, is true, but Q is false? What about when statement 1 is false and Q is true? That's what we're doing, right? Anyway, so now, P implies Q. Whenever you have an implication, if both are false, the implication itself has not been damaged, therefore still remains. So in this case, both are false. That makes it true. All right. And then we have when both are true, it's also true. And if the first part is true, but the second part is false, then it's false. If the result is true, think of it as the result or the outcome. So the effect. If the effect is true, then it still stands. So we have P is true, and that's good. And now we have not P or Q. So we have one or the other or both. So if we can look at it, true, false, true, true. All right, so if you look at it, yes, yes, these two match up. Check the back of the book. Okay. 2.63. Yes, true. Yes, yes. Good. All right. Next. All right. All right, let's go with 5. Okay. Not P or Q or R is equal to not P and not Q and not R. So that means when I say equal to, that means every line of the truth table between them, as you've seen already, has to match. When the line 3 of the first statement is true, it has to be true for the second statement as well in this case. Or that the particular T's and F's have to have the same one for each line between these two statements, between this one and that one, the results in the truth table. Now, we have 3, so we have 8. What else do we need? We need P, we need not P. Okay, let me just think about this for a minute here. What do we actually need? P, Q, R, not P, not Q, not R. We need P or Q or R, not P. Oh my goodness, this is going to take a while. All right, I'm going to change my pen's font size because we're going to be here for a while. Let's start at the back here. P, Q, R. Not, we might not need all of these, just so you know. But we're gonna do them all here. Not R. Okay. And then we need P. Or Q or R, not P or Q or R. And then we're going to need not P and not Q and not R. All right, that, make sure we have everything we need here. P or Q or R, not P or Q or R. Yes. Looks like we have everything we need. Let's do this. All right. Well, let's see this. So, again, true, 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 false, 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 false. Okay, good. Now then we have true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. Okay, so that just creates the basic all the variations between the three of them. Then we're going to start inverting them and doing stuff to them. Not P. So then first four F's. F, 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 T, 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 T. Okay? Not Q. We just flip them. F, F, T, T, F, F, T, T. Okay, make sure, getting especially these first six right and not making any major mistake is important, especially important. Otherwise, we just won't recover from it. False T. Okay, false, true, false, true, false, true. So, well, we took the first ones and we did the knots of them. Check them to make sure it's right. False or true, false or true, false, true, false, true, false, true, false, true. Okay, now we have P or Q or R. So at least one of them has to be true for this to be true. We have P, Q, and R. All agree. Well, the first four automatically are true because at least the P is going to be true in those four. Okay? How about if you look at, okay, they're all true except for the very last line, because you can see there's only three F's at the very last line. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. 6, 7, 8. Okay. We only have these three F's down here to give us an F. As long as one of them is true, the statement as a whole is true. Okay, good. Now, not that. We flip it. They're all false except for the last one. False, 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 true. Okay. So now we have not P and not Q and not R. Where do all three, now on an and, you have to absolutely agree, right? There could be no breaks in this chain. So that is only down here. So that's it. That's going to be true. Everywhere else, there's at least one F. So we're going to say F, 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 that's 4, 5, 6, 7, 8. So we can see this and this, they agree. Nice. Okay, it took a while, but it was worth it. All right, let's take a look here. See what the book says. Yep. Okay, now like a lot of this, you know, like this kind of a stuff, I would have to make several of logical mistakes in a row that, you know, I'd need a double negative to end up with the same result. Otherwise, like the fact that like I'm able to prove that it works is really enough that I wouldn't need to check the back of the book, but I just do it as a habit and just because sometimes maybe I made some like major leaps. I've had that one time where it's like I got a complicated question wrong, but completely by making incorrect assumptions. And I'm like, hey, teacher, can I still get the credit for it? He's like, no. Yeah, that was one of those. It wasn't in this class, but yeah, it happens. All right, 5. Here we go. Wait a minute. No, we just did 5. That was 5. 7. So we have P and Q. All right, so this, again, no matter how many times you flip them around, because there's only 2 statements, there's 4 variables. And I'm going to go back to my thicker pen here. I'm going to write P implies Q is equivalent to, see, when they give you a very complicated statement like this, P and not Q implies Q and not Q, right? They give you something like a word salad of that kind of a thing, and you have to, like, for example, if P says get A, and it's like this. Let's actually do this. Okay, let's see. P get A. Right, so what would the first one say? So P implies Q. I'm taking this aside just to show you how all this works, right? You know, like I already got a feel for it. I'm not an expert or anything, right? But I'm just showing you how this can work. We can plug things in just like an X and Y and other math. So P implies Q. So we're gonna say if get A is true, graduate is true. Okay? If get A is true, graduate is true. Also, if get A is false, graduate is false. So right now, let's work around the second part of it. Again, this is not answering the question. I'm simply showing you how this reads, and just for fun. Okay, so we have get A and not graduate implies, okay, so graduate and not graduate. So so the way this works is, by the way, I'm gonna write this in here. false statement. Get A and not graduate is a false statement. Implies graduate and not graduate. Also a false. So you see how that works. It's true that both statements are false. And it's true that the first two statements are true. So like if someone gave you this and says, if you get A and you will not graduate, and this is false, and you graduate and you not graduate, this is also false, then in a roundabout way, getting A, when that's true, graduating will also be true. That's basically how that works. I know it's wild, but trust me, when we have to do proofs, this stuff is going to be really handy. Now, let's do some of this stuff. Nope, left myself enough room. P. I need P implies Q. I probably don't have enough room. Okay, let me actually start a new page. Yeah, because I will not have enough room. It'll be just a word salad here. So let's just write this one again. P implies Q is equivalent to P and not Q, which implies Q and not Q. You can't have a Q and not Q, by the way. You can't, when you have a statement and it's not statement, the ands will always be false in that case, because something can't be both true and not true equally in this case. So let's keep that in mind. So that's a false statement. This right here, that's a false statement. So basically, this is a false implies falsehood. Truth implies truth. That's basically what it's saying. But let's actually do this. So we need P, Q. We need not Q. We need P. We don't need a not P. That's the only one we don't need here. P, we need P implies Q. P and not Q implies Q. Actually, we need P and not Q. And we need Q and not Q. Okay, so let's do this. I'm going to say P, Q, say not Q, say P implies Q, P and not Q, Q and not Q, and P and not Q implies Q and not Q. All right, and let me just start breaking these up. Four, one, true, true. So let's spread these out a little bit. It'll be a little easier to read. True, true, false, false. True, false, true, false. Not Q. False, true, false, true. P implies Q. When both are false, it is true, because the statement has not been harmed. And it's just, this is an implication. Just remember that. When you have a statement implying another statement and they're both false, that does not affect the original statement. The truthfulness of it remains. So then we have when they're both true is true, and then we have false, false. Okay, P and not Q. So on an and, they both have to be true. So okay, P and not Q is only true on the second line. True, false, P and not Q, false, false. Yeah, it's only true on the second line. False, false. Q and not Q. There's none of that. So this is going to be false, 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 false. Okay? And then we have P and not Q implies Q and not Q. When they're both false, this is true. When they're both okay. I wonder if I made a mistake somewhere. Well, I'll figure it out in a minute here. Yeah, I think I made a mistake earlier, but I'll fix that. It's not a big mistake. All right, false, true. That should be the correct. So I'm thinking this is where I made a mistake. That should be true. And let's find out. P implies Q. That's right. That's right. Because we care about the Q. We don't care what happens with the P. As long as the result happens, it's fine. So yeah, that technically was a mistake. Now the fact that I was able to quickly catch and realize that, rather than just submit it and be like, okay, well, it doesn't work. No, this stuff's important. You have to understand what's going on, and you could only understand by putting pen to paper. All right. You can't just by like listening to streams or whatever. You could watch the stream 10 times in a row, memorize it. But when it comes to sitting down, there's going to be important bits and pieces that are missing. You'll have to do it yourself. You have to at least copy down what I'm doing. Even if you don't understand it, it'll sink in. All right, so now if you look at it, this matches with that, right? Let's take a look. True, false, true, 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 false, true, true. Yes, okay, good. And then, okay, right, we have, right, I'm losing my train of thought here. We have, that was 7. Now, 9, decide whether or not the following pairs are logically equivalent. All right, let's look at 9. 9. So we have P and Q and not P or not Q. All right, well, P and Q, so let's just do this. So we need, okay, let's just write out everything we need, just like we always do. P, we need Q, we need not P, we need not Q, we need not P or not Q, and we need not P or not Q. All right, let's do this. I believe we have everything we need here. I missed one. P or Q? P and Q. That's the only one that I missed. We still need that one. Let's see. PQ, not P, not Q. P and Q. Not P or not Q. Not P or not Q. All right, let's do this. True, true, false, false, true, false, true, false. Wait a minute. False, false, true, true. Q, false, true, false, true. Not P or not Q. One or the other or both. When they're both false, it is false. But this is true, and this is true. Okay. And then we have not P or not Q. So we invert what we have here. We're going to say true, false, false, false. And then when P and Q are true, that's the only time they're true on an and. If one of them is false, 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 false. Okay, yes. Let's say yes, P or Q, and not P or not Q are logically there we go. Yes, that's what I'm reading. All right, let's check. Yes, what they did was they just pulled up the De Morgan's law on 9 and just used that. There you go. Instead of all this nonsense that, me having to write up the whole thing. If you look at De Morgan's law, yeah, because so let's just take the De Morgan's law. Remember, when you take this on a De Morgan's law, if you take this not, and we're gonna say not P and not Q. Let's apply it. Let's drop this in here. Double negative makes a positive, and this gets flipped, which is equal to P and Q. Wow, that was easy. What do you know? We could have just done that, right? We could have just put it in there, flipped the sign, and voila, we got a result we wanted. But hey, whatever works. Yeah. So that was fun. Let's continue on. All right. So that was 9. Let's look at 11. All right. All right, what do we got? I'm going to see if I can solve it by one of the laws we're given instead of writing up truth tables. And if I can't, then I'm going to use a truth table. It's just like if I could see something that makes a lot of sense. Not Q implies P. That's a terrible implication. Q implies P. Okay. Not P and P implies Q. So they both have to be true. And not Q implies P. Which rules can be used for this? Contrapositive looks like. It might be contrapositive. P implies Q, not P implies Q. If we take the contrapositive rule, and then we make it a not, we're going to say, so this is going to, actually, let's think about this. On a contrapositive, see, the problem is that we have P implies Q, and here we have, we have P implies Q, which gives us not Q implies not P, and we're going to say not P. Yeah, I don't know. It feels like we can do something with a contrapositive law, but honestly, by the time I figure that part out and I can make it bulletproof, I might as well just write up the truth table. Sometimes the simplest approach is the best, because we don't know if this is true or not, right? I mean, we could have an opinion. We think this is going to work, but then, we start messing around with it, and it could be false, and then we have to falsify and explain why it's false. And then just write the truth table. That's totally fine. There's nothing wrong with that. And then we're going to say P implies Q, and I mean Q implies P. Oh boy, this is going to be a long one. Small font again. Small font. Okay, we're going to go with P, Q, not P, not Q. We're going to say P implies Q. Say not P, and P implies Q. All right, that covers all that. And we're going to say Q implies P. Gotta be careful adding additional accidental symbols there. And we're going to say not Q implies P. All right. So like I said, this is kind of a complicated one. I don't want to reason through it too much. I'd rather just prove it by truth table. And there's nothing wrong with that. So if they just want a result, they don't say, hey, you can solve this. Well, yeah, it might be solvable by using the other ones. We're just going to do it this way. Because I have to prove it. I don't just have to say, oh, my hunch says this. No. But when we say we prove something, we mean that we have to demonstrate it. Proving something is you demonstrate it in such a way that it's absolutely true for anyone, even someone that's like your worst enemy, that there's nothing they can say that's like, oh, no, this is not like a matter of opinion or my hunch, or this is, like oh, it's beyond a shadow of a doubt. No, this is rock solid, okay? So that's what a proof is. It's a rock solid demonstration. We have true, and for all possible cases of the type that it refers to. You close all possible loopholes. That's what a proof is. That's why math is so powerful. All right. False, true, true. Okay, so we have true, true, false, 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 true. And we have false, true, false, true. Okay, P implies Q. Remember the rule. If we care about the result, the Q, and if both are false, it's true. That's true. We know that the Q is true. False, true. P implies Q. Yes. Now we're going to say Q implies P. The other way around. Now P is the one that matters. If P is true, let's see here. If P is correct, P is true, false, true. Okay, and then we're going to say not, false, false, true, false. Okay, and then we're going to say not P and P implies Q. They both have to agree. P implies Q. So we need this, and then we need this, and then we need an and sign between them. All right. So where are they true across the board? We have true and true. This is true. We have true and true. This is line 3 is true. Line 4 is false. And not P. This is, and this is false. And then we're saying false, false, true, false. This is close. I want to double check my work. So not P. That's correct. P implies Q. P implies Q. Both are false. That makes it true. Yes, that is correct. So these two are correct. So then this is correct. Let's see here. Not P and P implies Q. So that should be correct. And over here we have Q implies P. Let's look at what Q implies P is. Q implies P on the last line is when Q implies P, they're both false, right? So that would still be true. And it's an inverse of that, it's false. So no, I would say that see, this is why we had to write a truth table. Instead of messing around and trying to use contrapositive and De Morgan's laws and trying to stitch them all together, this is more visual, and then we can find the one case where they don't work. And I would say no. No, the statements are not equivalent. All right, let's see what it says here. The columns for the do not quite agree, thus the two statements are not logically equivalent. Yeah. They're like not quite agree. They don't agree. If one iota is off, no. It's not logically equivalent. And in terms of how I wrote it, my columns agree with their columns. So yeah, they went with PQ and not P. They didn't do not Q though, but it doesn't matter. Like you can do more, you can do less, as long as your final columns, the columns for this part and the columns for this part, are what the book says. That's all that really matters. All this work that we do beforehand is to get to that part. So that's good. All right, let's do 13. All right. Okay. All right, so we're going to use small font again because this is going to be another long one. All right, so we have P. Wait a minute. Let's see what we have here. P. Well, let me write this out first so you can see it for yourself. And I'm going to see if there's a quick way we can, any of the above laws help us out. So this right here, this looks like an associative law. P or Q and R. So we have P or Q and R, or P or Q and R. Yeah, so it appears this is, hang on a minute. What can we use for that? This is 13, P or Q and R. P or Q and R. P or Q and R is equal to P or Q and R. Looks like a distributive law, actually. Yeah, let me just make sure. I want to jump ahead of myself here. Distributive law, P or Q and R, and P or Q and R. And P or R. Yes, we can use a distributive law. Let's write it out first. And then we're just I'm gonna explain. This is a fairly simple one. We have what's it gonna say? Yes, by fact 2.4, the states we need, which one was this? P or states P or Q and R is equivalent to P or Q and P or R. And then we're going to say that, so basically the first part completely lines up. The second part, because it's an and, okay. P or Q and P or R. For the, yes. And because it's an or, in cases where, which permits, comma, which permits P or Q and P or R, which permits there. Which permits, no, wait a minute. Let's not just overthink this here, just write this. Yeah. Which, we shouldn't use the word permits. I should say problem covers. That's how I'm going to say it. All right. Wait a minute. Okay, so okay, so no. Actually, I was wrong there. This is why using the 13 here, let me see here. Yeah, no, 13 is wrong. And that's because I assume that you can take that case and that's how they got me though, by the way. That's a good point. See, it's P or R, but then I just dropped the P and use the R for cases where R exists, but I guess you can't do that. So let me take a look at it. I'm going to look at it one more time, make sure I didn't misread something. It is wrong though, and I want to make sure why I get this. P or Q and R equal to P or Q and P or R. So in that case, the R can be false if P is correct. You can't drop this. That's what I did. I dropped that, and you can't do that. So going back to our old friend, the truth table. Okay, nothing gets past the truth table. P. So we need P. Let's try Q, R, and then we need, let's see here, we need Q and R, P or Q, and we need P or Q and R, and we need P or Q and R. All right, let's do this. Go. Okay, let's make sure that I have all the variables that I need. PQR, yeah. I mean, P or Q and R have it. P or Q and R have it. P or Q, and I need Q and R. I have it. Okay, let's do this. Okay, true, 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 false, 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 true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. Both Q and R have to be true. True, false, 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 true, false, false. Gotta start checking to make sure I'm not being sloppy anywhere. Looks right. Okay. P or Q or both. True. True. This is true, true, true. First four are going to be true. 3, 4. Only the last two are false. Okay, and then P or Q and R. So where are they false? P or Q and R. The first four are true. True, 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 true. And then we have false. This is true. Wait a minute. Q and R. Q and R. This is true. Line 5 is true. They're both. I'm sorry. Q and R is true on line 5. 6 and 7, they're both false. And 8 is false. P or Q and R. False. False, false. So let's check that one more time. True, 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 true. Q and R is true on line 5. Last 3 are false. Okay. And the last 3 are false. Q and so yeah. So last 3 are false. False, false, false. Okay. P or Q and R. So we are true on the first line. R. False. True on the third line. False. True on the fifth line. A minute. Okay, 6th line. They both have to be false, false, false. False, false, false. Check it again. P or Q and R. True on the first line, false on the second line, true on the third line, false on the fourth, true on the fifth, false on the 6th, 7th, and 8th, also false. So now we're looking at these two. We have yeah, no, they don't match up. They match up somewhat, but as you can see, line 2 between here and line 4 here, they are not logically equivalent. No, the are not okay, and that answers it. There is no truth table for this one. They simply demonstrated by by using logic, in the sense that they let me actually read you the book's answer. Are not logical equivalent because if P is true and Q equals R equals false, then the first statement is true and the second statement is false. So yeah, this way I just showed it on through the lines, and yeah, so basically, yeah, that's the end of this chapter. We are done here. Next we have is quantifiers 2.7. Okay. All right. Well, hey, we did very well. Looks like we'll have to continue this tomorrow, probably. I'm gonna try to get through a bunch of this stuff quickly. All right. Yeah, I have to work first thing in the morning, so otherwise I would love to keep going. I hope you guys enjoyed this parasocial stream, and I will see you next time.